Yes, I just started recording, so maybe I should do that again since I just now started recording. I forgot for the introduction. So yeah, we're happy to have Ling Long speaking today, and she will be speaking about a Whipple formula revisited.
All right, thank you for the opportunity. So this is a new project just finished. We posted to archive. It's joined with Winnie at Penn State and my colleague Fang-Ting too. And let's see. So basically what I'm going to talk about is under the umbrella of hypergeometric objects. So they include classical hypergeometric functions that Sharon and I start working on those things at Wien. And also there are Galois perspectives to hypergeometric objects. And there are also character sum identities. And another side will be the p-adic side. So a lot of people got involved. I don't have enough time to mention everything, but the slides will be here. And basically, I want to use kind of the paper. It's pretty kind of a lot of things going on. So I picked one particular angle. So I will concentrate on this kind of perspective. The major motivation for at least myself will be there are many existing formulas available, including Clausen formula, and Whipple have a few very nice formulas. They are actually formulation over C. And what I'm interested in is to interpret them in other settings and then use them to solve open problems if all possible. So for this talk, a particular motivation will be to construct decomposable hypergeometric motifs or decomposable hypergeometric Galois representations. So which will actually give rise to some connections to supercongress, hypergeometric supercongress that probably I won't have time to talk about. And to start with the setup, there are two things of fundamental importance. One is the gamma function. And in the finite field setting that I will be focusing on, so the setup will be if I have FQ, which is a finite field of characteristic T, and which is assumed to be off for this talk, and the set of all multiplicative characters is forming a cyclic group. So we will choose omega to be a generator of this multiplicative group. If you have any kind, which is also multiplicative character, so it will be this generator raised to an integer power. And the finite field analog of gamma function is Gauss sum. So it's defined by, you actually put together the multiplicative character, and also the zeta p denotes a primitive piece-root unity. And then you have the trace function. If you pick out any elements which are invertible in FQ, you apply the trace function, you get a value in FP, you put that into the power of zeta p, and then you put together like a convolution, you get the Gauss sum. So the Gauss sum has a lot of very basic properties that are useful for our discussions. And now let me get to basically when I refer to a hypergeometric data. So I mean a triple consists of two multi-sets. So the elements in alpha is denoted by A1, A2, etc. So they are rational numbers. The second multi-set in the classical setting will be the lower parameters. We'll start with 1, which is a convention, and then B2, B3, etc. They are also in my talk will be rational numbers. So the convention will be the first one, it's 1. And the third kind of element in the hypergeometric data is lambda. Lambda for this talk sometimes are algebraic numbers. In general, you can pick that to be any complex numbers. And once I have just two multi-set alpha, beta, the elements could repeat. And we will denote the least positive common denominator of all AI and Bj to be capital letter M. Because eventually when I get to Galois representation, the underlying field will be the cyclotomic extension Q joining this primitive N through O1. So which is the underlying field, basically, we are going to work with. And also the notation, if we call alpha to be self-due, which is going to be the condition we're going to impose, it's the fact if you construct this polynomial in actual variable capital X, and then you use those A, which are rational numbers, you make modular unities, and then you multiply together. If the coefficient turns out to be a real number, which means it's going to be the cyclotomic field intersecting with real number, then alpha is said to be self-due. And further, if the coefficients of this polynomial are integers, then we say alpha is defined over Q. So the notation is /Q. And here's 2 examples. If you look at the multi-set consists of 1/5 and 4/5. If you multiply out, you get a quadratic equation. And the polynomials are going to define over Q joining zeta phi and zeta phi inverse. So it's self-due. So self-due later, the important thing for kind of useful thing to remember, self-due means if you see 1/5, then 1 minus 1/5, which is 4/5, will be in the set as well. And if you look at this, the first example is not defined over Q, but if you move on to the second example, 1/2, 1/3, 2/3. This case is defined over Q because when you multiply out, essentially you get x plus 1 and also the cyclotomic polynomial of degree 3. And if you look at the corresponding capital M, the capital M will be 5 for the first multi-set. Capital M will be 6 for the corresponding multi-set for the second one. So this is the notation on a single multi-set. If you put together, going back to hypergeometric datum, so it's said to be primitive if among the alpha and beta, the parameters AI minus BJ are not integer for any choice of I and J. So this is the notion for primitive. And we're going to see an imprimitive example later in Whipple's formula. And so this triple is said to be defined over Q if both alpha beta defined over Q behaving like the second multi-set, and lambda is also defined over Q. And the pair alpha beta in a weaker condition are said to be self-due if both alpha and beta are self-due, in the sense that if you have A in alpha, 1 minus A is also in alpha as well. Okay. So now you have this given hypergeometric datum, then you can compute a few things. I'm going to mention 3 over here. Over C, you can compute the classical hypergeometric function. So basically, it's going to be a formal power series in terms of lambda. So lambda, the power in the untruncated case will go from 0 to infinity. And the coefficient are actually kind of computed using rising factorial and further in terms of the gamma functions. And if you consider lambda as a formal, it's a variable, if it varies, then as a function of lambda, it satisfies an ODE. If you avoid the singularities, which are 0, 1, and infinity, the local solution at any regular point, if you look at the holomorphic solutions, they are forming an n-dimensional C vector space, where n over here is the length of the multi-set alpha, which is the same as beta as well in this talk. So the second thing we're going to touch briefly will be the truncated series. So it's the same notation. If we put the subscript n over here, that means, choose a wrong one. It should be a different one, all right? It's unrelating to the length, but it just happened to be that. All right, it's going to be, if I put down a subscript, all right, should be, say, something else like S. So it's a truncation from K from 0 to S. And then the third one, I'm not going to get to the details, but it's going to be the finite field analog. So over the finite field FQ, and here I'm going to first impose the condition. The size is going to be 1 modulo this capital M over here, depending on the denominator. If you have lambda, which is also in the finite field, then notice by our choice of capital M, this will actually assume AI, if you further multiply with Q minus 1, it will becoming an integer instead of a rational number. So you get all the upper parameter boost up to integers, the same for the lower parameter BIs. Then you put them together in this formulation, which is pretty much the finite field analog of the classical hypergeometric function. You get to so-called the hypergeometric sum associated with the hypergeometric datum alpha, beta, lambda, and depending on Q. And another thing I would like to mention is if alpha, beta, lambda are all defined over Q, so you can do the reduction of lambda to any finite field you like. And in the work of Fritz Boykers, Harry Cohen, and Anton Mennett, they rewrite the right-hand side of the finite field version in terms of using multiplication formula. So they get to a version which is independent of the condition we put on Q to be 1 modulo the capital letter M. So the character sum can be expanded to almost all P, in which cases, if the hypergeometric datum is defined over Q, the value will be an integer, or it's a rational number in general. Any question before I move on? All right, so here is one kind of systematic way if I want to go. The previous slide, we talked about individual finite fields, but you can go from the classical setting to individual finite fields in a more systematic way. So the way to go is you start with the same setup, and then here we're going to denote the Galois group, which is the absolute Galois group of the cyclotomic field. And shorthand notation will be either I put G with the field, or it's going to be G of M, which is the absolute cyclotomic field of the Q joining zeta M over here, G of M. And if we choose lambda in this setting to be one of those cyclotomic integers, not including 0, so what we will do is for any prime ideal P not dividing capital letter M, we can look at the corresponding residue field, which is going to be, P is going to be unramified. So we're going to look at the residue field and assume that the Q is the size. And by the choice over here, which is unramified, automatically we are creating residue field, which is the size is 1 modulo the capital letter M. And for the generator, for the corresponding multiplicative characters, one kind of systematic choice will be I require this generator applying to the primitive answer modulo P in the finite field is going to be the primitive answer to the -1 power. So this is actually the way I'm going to fix the primitive generator for individual residue field. So then you'll use what we laid out in the previous slide. You can construct a finite field version of the H function. And now if I use this convention for the choice of the primitive character, we're going to suppress the omega. So it's going to be only depends on alpha, beta now, and also the residual field. Essentially depends on the non-zero prime ideal. And another version of hypergeometric sum, which is useful if I'm able to get to the proof, is the period function. All right. So they are pretty much closely related. I might use that later, but I'm not going to define that. All right. So the spirit will be give you the hypergeometric data. You can compute many different things very explicitly. So let me give you some of the motivations, what we're doing over here. If we start with any fixed complex number, which is C, removing 0 plus minus 1, for fixed K, we get to this elliptic curve. So it's double cover of CP1 removing 4 points. So the singularity occurs to when K is going to be plus minus 1. And the ramification is plus minus 1 and plus minus 1 over K. So this is elliptic curve. And if you fix a k, it's a single elliptic curve, but if you let k varies, you have a family. So it's a fiber space. So in particular, some fibers are degenerate, including 0, plus, minus 1. So these are the degenerate cases. And if you avoid the degenerate cases, the rank homology of this elliptic curve, you can compute it using two differentials. So they are differential of first and second kind on the elliptic curve. The first one, which is this one, dx over y, it's holomorphic. So it's a unique up to scalar for the first choice. The second choice is not holomorphic, but one particular choice is this one over here, is dx over y, and in front of it, you multiply 1 minus k squared x squared. So once you have these two differentials, you can compute the corresponding periods. So one pass is going from 0 to 1. And if you look back, you get a pass, which is going to be a cycle on the elliptic curve. So this, the integration over here, 0 to 1 for the first differential, and you get to the classical hypergeometric function, and the parameter for alpha will be 1/2, 1/2. The parameter for beta is 1 and 1. And in the classical setting, it's written the upper parameters goes up. The beta parameter goes down because beta 1 is 1, so we remove the 1. There is a hole over there. And the notation over here is 2 and 1, indicates that there are two elements upper. And actually there are two elements down, but one is chosen to be 1. So there is only one freedom down here. So the second one, which is going to be the second differential of second kind, you get to the complete elliptic integral of second kind. So the form is pretty similar, but this guy over here, you're getting something of a complete elliptic integral of second kind, and the relation in between will be the second one can be attained as derivative of the first one and plus a scalar multiple of the first one. So when we get to Whipple's formula, a similar situation is going to happen to this one over here. And of course, when we get to the specialized situation, when k is a rational number, which is not 0 and plus minus 1, so you have Galois representation, which is two-dimensional, coincide with the length of the alpha set. So the length of alpha set is 2, consists of 1/2 and 1/2. And for unramified prime number p, you can compute the trees for the corresponding Galois representation for Bennett's conjugacy class at p. And for this particular case, it turns out to be the character sum HP 1/2, 1/2, 1, 1, and k squared. Right. And also, of course, in this setup over here, we know elliptic curve is modular. So the modular form will actually come into the picture as well. Okay. Any question before I move on further? All right. So basically, it's summarizing in general what happens to the previous picture is as follows. If you have alpha, beta to multiset, if you assume they are primitive, if you know m is the least common denominator, and if you fix any lambda over here for convenience, I choose that to be an integer, which is not 0. And if you fix L, which is for the Elliptic representation, and there are other assumptions, including how many elements in beta are in Z. And with all such basic assumption, then what we can conclude is there is a finite dimensional vector space. All right, it's L-adic vector space of this cyclotomic field Galois representation. And basically the spirit will be again at unramified prime. You can compute the trees. The trees essentially is the H function. Okay, there is some decoration over here and some power of Q, which is the residual field size, possibly with additional character, but I'm not going to get to the details over there. I want to point out that when you get to the generic fiber, avoiding 0, 1, which are the singularities, then generically the dimension for this vector space will be the same as the length of the multiset alpha. So the length of multiset alpha determines generically degree of the Galois representation. And generically, the representation is also pure in the sense that if you look at the characteristic polynomial of Frobenius, and the roots all have the same absolute value, which is q raised to n-1/2 over here. And at the degenerate fiber, including lambda equals to 1, so lambda equals to 1 is the one we are most interested in. The dimension has one dimension drop down from n to n-1. And further, this guy has a subrepresentation. The subrepresentation is more or less the same as n-1 or 1 lower, depending on this is n is going to be even or odd. So the primitive part will behave very much like the representation mentioned in B. For example, later in Whipple's formula, the length of alpha after reduction will be 6. And if we put into this formula, it will be 6 minus 1, 5 over 2, 2.5, floor function 2. So you get to the primitive part for the representation will be 4. But here, C tells us at fiber lambda equals to 1 is 5-dimensional. So a priori, we already know there is a decomposition going on. So it's going to be 4 plus 1. This is the primitive decomposition for the corresponding Galois representation. And in addition, if we know that hypergeometric datum is defined over Q, then this representation a priori is for the absolute Galois group of the cyclotomic field. And in this case, all the HP functions are integers. And the whole representation, the representation can be lifted to GQ for the big Galois group. And one of such lift is given by the HP function, the generalization using multiplication formula. So this is the preferred choice. It's not unique, but this is the preferred choice for the computation. And if you get to MAGMA's implementation by Mark Watkins for hypergeometric motif, that's the one he's actually computing as well. All right, so finally I can get to Whipple's formula after a long preparation. So this is the Whipple's formula, which is actually a nice formula relates 7f6 with value at 1, and on the right-hand side, 4f3 with value at 1. And in between, there are some gamma factors. I'm not going to focus on that. But on the left-hand side, so there's a 7f6. Firstly, if you look at the formulation over here, the alpha set consists of alpha, consists of A, 1 plus A over 2, C, D, E, F, G. And the beta set consists of 1, A over 2, 1 plus A minus C, 1 plus A minus D, etc. So it's not primitive because this A2 minus B2 is 1. So it's imprimitive to start with. And if I get to the finite field version, this means the finite field analog of these two characters will be the same. So there will be a cancellation in the finite field version. So it will drop down from the length of alpha being 7 to 6. 6 will be the more essential one. And the hypergeometric parameters on the left-hand side is also well-posed. Well-posed means if you add the corresponding column over here, it's A plus 1 is 1 plus A, 1 plus A over 2 plus A over 2 is 1 plus A. So you have 1 plus A here, 1 plus A over here. So this is the situation which is called well-posed. And in another word, if you write down the upper parameter in terms of A1 to A7, beta can be simply written as 1 plus A minus AI. So this is another word to say that it's well-posed on the left-hand side. And this Whipple's formula is widely known and used as well. I myself use in a few different papers to attain supercongruence, which is actually one very convenient formula to use to have around. And now I'm going to impose the self-due condition on Whipple's formula. The reason is because if I want to get to Galois representation, self-due is one very nice property to give me good representations in the end. All right. So to impose self-due, firstly, I cancel out these two in the finite field case. They correspond to the same thing, so I cancel that out. So we get 6F1 reduced from 7F6. If I want to make it to be self-due, essentially, let's focus on alpha set first. So it consists of A, C, D, E, F, G. Self-due, as I mentioned, essentially means you have A, then 1 minus A should be there. And for this reason, I set C and D sum to be 1, and E and F sum to be 1 to make conveniently self-due objects. All right, of course, it's another thing I should probably do is the relation between A and E. But before we go further, we notice that in order to make beta to be self-due, and beta is 1 plus A minus AI, if I already made alpha self-due, I do not have too many options for A. A essentially could be only if it's 1, but it's in primitive. I do not like the choice, so A, if I want a primitive choice, A will be 1/2. So this forces E to be 1/2 as well. So that's why later we specialize A to be 1/2, C plus D to be 1, F plus G to be 1, and E to be 1/2. But 1/2, we're going to get into trouble that one of the gamma value will be 0. So we do a little bit deformation. Right? So subtracting P over 2, where P in my mind is an odd prime. So I'm getting a negative integer, so both hand side terminates. So this is a happy situation. Okay. All right, so we get to, applying basically the construction to, if I want to get to something self-due, this is what we will do. We get to a hypergeometric data on the left-hand side, it reads as 1/2, C, 1 minus C, 1/2, F, 1 minus F. So this is the alpha set on the left-hand side. The beta set on the left-hand side reads as 1, 3/2 minus C, 1/2 plus C, 1, 3/2 minus F, and 1/2 plus F. All right, this is the beta set. The argument over here, lambda is 1. And on the right-hand side, then it reads as 1/2, 1/2, F, 1 minus F. And then the lower parameter reads as 1, 1, 3/2 minus C, and 1/2 plus C. And then the argument is also 1. So we get to this formulation. And actually, in the later, if I have time to get to the proof, there are two other players which will play a role in the proof. One is another hypergeometric data. Essentially, for H2, I delete one copy of 1/2 from alpha and delete one copy of 1 from beta. So we get to HD3. So this is going to be give us, in a classical case, a 3F2 hypergeometric functions. And here the argument can be any variable x that I like. And this particular hypergeometric function 3F2, which is self-due, enjoys a very unique property, which is called the Clausen formula. So the self-due property makes this 3F2 to be a product of 2F1 functions. And the parameters for these two 2F1 functions, if you compute it, that's what we computed, is in terms of C and F. We do not see E, which is 1/2. And then B is going to be the C1, or C and D. D is 1 minus C, etc. So we only need C and F, two variables. Okay. And now we're going to look at the least common denominator for the 2F1, which is called the capital N over here. And the least common denominator for HD2, which is the same as for HD3, is capital M as before. And we notice a relation between these two integers. They're actually pretty close. So this typically is maybe bigger than the first one, but it's at most double of the first one. In terms of Galois representation, what it means over here, it's if I look at the corresponding Galois group, it's a subgroup of the corresponding Galois group of capital letter M, but the index is at most 2, which is the observation. And now here's the Whipple's formula that in the version in terms of Galois representations. So it reads as follows. In terms of Galois representation, Whipple's formula, and in order to get a good version, we impose the condition that removing the other parameter using self-due assumptions, so there are only C and F remaining. So C and F are chosen to be 2 rational numbers. We further impose C and F are chosen so that both of the hypergeometric data on the left and right-hand side are primitive. So now they're both primitive and self-due. And we have 2 integers as discussed in the previous slides. From the first hypergeometric data, where alpha consists of 6 elements, but the argument is 1. And by the theorem, which is due to Katz, essentially says the corresponding Galois representation for any fixed choice of L, it will be 1-dimension job, so it's going to be 5-dimensional. There will be a primitive part, which is 4-dimensional. And similar story happens to the second hypergeometric datum, alpha. The length is 4, so the representation will be 3-dimensional, and it drops down to 2 + 1 according to Katz's theorem. So we discover if you actually further restrict, if necessary, of both representations down to this at most index 2 subgroup, then what you will see will be the 5-dimensional representation on the left-hand side. It's isomorphic to this 3-dimensional representation on the right, twisting with a cyclotomic character. So there is a Tate twist going on. And plus, this is 3-dimensional, so there's something else will be 2-dimensional and can be computed very explicitly. So this actually tells us that Whipple's formula, if you interpret in terms of Galois representation, it tells you that special choices under the assumption of well-posed and self-due, the representation is going to be decomposed into 3 + 2, and further the 3 will decompose into 2 + 1. So it has a decomposition in terms of 2 + 2 + 1 in terms of Galois representations. And then compared to the classical setting, so in the classical setting, after we put the self-due assumption, that's what you will see, that 7f6 and 1 agree with, there are some gamma factor, there is a p, there is the 4f3. In the finite field or in the Galois perspective, they are exactly parallel. You have the corresponding Galois representation after you remove all the redundancy. It's going to contain 1 factor coming from the right-hand side, and the p over here corresponding to the cyclotomic character at any p which is not L. If you compute the value at the Frobenius p, it's going to be p. So it's playing the role of this p up here. Okay. So let me actually further discuss how we use the theorem. So of course, in addition to self-due, we further impose the first hypergeometric datum to be defined over Q and primitive. So if I want something defined over Q, that means basically C1 minus C, F1 minus F. Put together, it's going to be forming a Galois orbit. So that requires the denominator of C and F. The Euler number could at most be 1, 2, or 4. So we drop down to the cases, the denominator could be Euler number either 1, 2, or at most 4. And the primitive condition remove the appearance of 1/4. So this is the complete list of all the possibilities. If you do not count the order, if you do not count the order, that's all they are. All right, so you get the 7 such kind of very special Galois representations. Then of course we can compute the corresponding modularity. Now everything's break down into 2 plus 2 plus 1. All of them can be lifted up to GQ, so you can look at the corresponding modularities. So then we computed the corresponding modular form for degree 2 pieces. And there are 2 degree 2 pieces. So in your mind, the second and the last row corresponding to the contribution from HD2. So the primitive part is the first one up here. And the notation over here is they use the L function modular form database system. So the A over here is the level, 6 is the weight. And then A and A will correspond to characters. So it says that for instance, if you pick C and F to be 1/2 and 1/2, the leading modular form, which is the outer one, will have weight 6, level will be 8. And then the middle one with a P in front of it will have weight 4, same level. And the degree 1 piece is P squared with a character 1. This is the legenda symbol. Okay. And the other cases, you can compute it in more or less the same way. And in the computation, we did use Mark Watkins' implementation of hypergeometric motif to identify the corresponding modular forms. Okay. Any questions so far?
I have a quick question.
Yep.
So just staring at this, there are a few cases where the weights of these forms are the same, but it looks like in general they're different. Is there a way, can you see
that's
that?
actually something, that's a very good observation. So we arranged that, see the first 3 cases, the leading weight is 6. And then the next few cases, the weight dropped down to 4. In that case, you need additional copy of P because I mentioned the absolute value for the primitive case will be all the same. For the first 2 will be P to the 5/2 if you look at the Hecker polynomials eigenvalues. Right. So this is actually the situation where in the theorem, if I get back to the theorem, in addition to the P function, there is also Q raised to length of the parameter minus how many integers in beta over 2. All right, that's where the contribution coming from. In terms of hypergeometric data, you can also draw the so-called zigzag diagram telling you the Hodge numbers. So for the first 3 cases, the Hodge numbers kind of going a peak, going down this way, so they have distinguished value. But for the other one, it just happens the Hodge number have some of the coincidence, so have some duplication going on, right? But everything can be explained explicitly. Okay, so if you have time, I can explain what's going on after I finish. Then may, okay.
Sounds good, thanks.
So, and as Ian observed that for actually for the 7 cases, only the first 3 cases might possibly have p-adic unit root, in the sense that if you look at the AP value, you want that to be not 0, the AP value to be not 0 modulo P. The unit root case only happens to the first 3 cases. And the second one always is a multiple P. The last one is always a multiple P squared. If you go down to the list, unit root do not happen to the other cases. All right, so this kind of give you a way to filter the data that we computed. And let's get back to a big kind of in the background. If we mention hypergeometric objects, I mentioned there are compatible package with different aspects. So let me mention some related topics over here. For the case of 1/2, 1/2, there is the case with possibly a unit root. So the leading term is going to be leading contribution coming from weight 6 modular from level 8. And this formula actually first proved by Sharon Frechette, Keanu, and Matt Papanikolaou. So they use actually, it's the Salvatrice formula. This is the way they prove this result over here. So we're using different approach. We attain 6 more cases. And regarding to the first one, which is a conjecture by Eric Mortensen, he conjectured that for the first one, there is a possibly in some cases, there is a p-adic unit root. If you look at the corresponding 6F5, all right, so this is after you delete 5 quarter and 1 quarter, and you look at the truncation at P is odd prime. If you do the truncation at P minus 1, you get a rational number. This rational number, he discovered amazingly, coincide with the piece coefficient of this V6 modular form. Modular a very high power, which is P to the 5. So this is a scenario which is actually later, David Roberts, Rodriguez Villegas, they make a conjecture of how high this power could be. The power is actually determined by the Hodge number for this corresponding modular form. There are 4 zeros in the middle as the Hodge number gap. So 5 turns out to be 1 plus 4. And now once we get to this result, this kind of formulation, we get to Whipple's formula. Whipple's formula, basically, I have to add back the 5 quarter and 1 quarter. And Whipple's formula corresponding to, if I change 1 to be t, this is actually the derivative of the function plus a scalar multiple of the function with a t. It corresponds to somehow like a differential of second kind. So when we do the same game with the 5 quarter, 1 quarter added back to the truncation at P minus 1, what we discover is actually, in this case, the truncated series will agree with the second term modulo P to the 4. And P to the 4, in this case, this is the waveform modular form. So the Hodge sequence is 1, 0, 0, 1. So 4 comes from, there is a P, additional P over here. So 1 plus 1 plus 2. This is how you get to the 4. And I forgot to mention that so Mortensen actually made the conjecture for the first one a while ago. And more recently, modulo P to the 3, the version was proved for all the odd prime by Robert Osborne, Armin Strauss, and Wading Suderman. And what I want to mention is, of course, for this kind of supercongruence, it's not easy to prove. Even for the first one, they managed to prove only P to the 3. It's actually pretty tricky. It's also very tricky to get to locate where you find those supercongruences. That's why I started the kind of, why the project was started at the first place. We want to find decomposable Galois representations so that the Hodge number gap might be big. Okay. So interestingly, what we should think about is that supercongruence down here is actually so-called the non-Archimedean version. If you do the truncation, it happens to agree with the piece coefficient. And then you wonder what happens if I do not do any truncation, right? So it's also sensible to ask, what if I do not do any truncation at all? So the untruncated version we prove actually, it's really some kind of periods for the corresponding modular form, which is the V6 for the first one, the V4 for the second one. And the path somehow corresponding to some modular function being absolute value to be 1, but it's written in this particular path over here. And so this is what we call the Archimedean version for the supercongruence. So they all coming in a compatible package. And the P over here actually is corresponding to the 1 over pi. Down here in the numerator, it's due to the Legendre relation giving you a copy of pi, and which is on the finite, the non-Archimedean version appear as a copy of P, which is very much like the Ramanujan supercongruence that we proved at the WIN project. So this is actually the applications for using Whipple's formula in this paper so far. And so let me quickly actually get to the idea of the proof. All right. So let me mention about the idea of the proof. Once we impose the well-posed condition, if we go to the finite field version, and we're going to use a different formulation, it's called the P function. The P function is the finite field period function that in my another project joined with Jenny Fuseli, Ravi Ramakrishna, Holly Swisher, and Fang-Ting too, we actually gave a construction for the finite field period function, which is very parallel to the classical setting. And the good thing is, if you let, say, this is the position for A, this is the position for E, and now we choose both of them to be 1/2. If A and A are the same for these two spots, and now you have well-posed theories, but it's off a little bit, that it's 1 plus A minus D, but going to this spot. There's some kind of shuffling going on. But you can actually undo the shuffling by a character, so it's not very major surgery. But the good thing is, once you do the shuffling, you can write the 6p5 at 1 in terms of summation over the finite field. You have put the A down here, and then it's a 3p2. All right, so in our mind, of course, 3p2 for generic choice of T corresponding to three-dimensional Galois representations. So if we additionally assuming this 3p2 is self-due, there is the finite field analog of Clausen formula attained by Ron Evans and John Green. So it says that if you get to the finite field version of the Clausen formula, in this formulation, phi is the quadratic character. So it's a self-due. You have eta. Eta bar is the inverse, so it's a complex conjugate. And you have K and K bar. This three-dimensional Galois representation is the tensor product of this two-dimensional Galois representation in the background with another two-dimensional representation in the background, subtracting a one-dimensional Galois representation. So the three-dimensional one essentially is a tensor product of two, subtracting one. And when you look at what happens, the argument goes to 1. As what we mentioned, in this case, argument being 1 indicates the representation will have a one-dimension drop. So this is the CM case. If the argument turns out to be 1, it's going to be sum of two one-dimensional Galois representations. Right, so it drops down. So now we put our lemma into the setting for the P function for HD1 involving 6 AIs in alpha and 6 BIs in beta. So it's going to be of this form, that the P function we're going to compute is going to be summation over everything in the finite field, the quadratic character, and then these three-dimensional representations, chase square. And don't forget that chase square, if it's coming from a three-dimensional Galois representation, the square means I'm going to do the tensor product of the corresponding representation with itself. And once you do that, then you'll notice automatically the representation decomposes into symmetric power and alternating power. Symmetric square is going to be 6-dimensional, alternating square is going to be 3-dimensional. And it's a very special case because of the Clausen formula that alternating square is actually very close to the determinant. So you get back, it's more or less Q times itself up to this additional character. If you put them together, the contribution from the second part will involve the P function, and there is the Q you can put to the front, and applying the quadratic character T and 1 minus T to the front as well. And putting together using the inductive formula for P function, you get to the HD2 involving 4 elements. So that's how everything put together to get to the main idea for the proof. And thank you for your attention.
Great. Let's thank Ling for her talk. Does anyone have any questions?
Yeah, I have a question, Ling, about your the last slide on your applications.
Mm-hmm.
So you relate these hypergeometric values to these integrals along this geodesic between these two CM points. It looks a little bit like a cycle integral, like if you would connect 2 points. Yeah, okay. So what I'm wondering then is, like, since those are connected to L values, do you also like get some formula for some L value from these, or?
That was actually part of the motivation, is to write as L value, but somehow L value it's more restrictive because the path is from 0 to infinity.
Mm-hmm.
And then if you look at cycles on modular curve, the cycle could go more general than 0 to infinity. So we try very hard to convert it to L values, but this is a more general form. In the end, we concluded in most of the cases, that's what you will actually attain. Of course, this formulation look a little bit kind of arbitrary. In the end, it's not, because if you, from the transcendental theory, you have a different, and you have more modular form. You look at the corresponding integration, the cycles, the dimension of the cycles is depending on the genus of the modular curve. It's actually in the transcendental theory, the right-hand side is living in a finite dimensional vector space over Q bar. So the coincidence between the left and right-hand side is actually very rare in general. It's actually super compatible with what we discover, above.
Okay, thanks.
Any other questions?
Yes, I have a question.
Yes.
George Andrews proved a generalization of Whipple's formula. Instead of having a 7F6, you have a 9F8, you have a double sum. Or instead of a 9F8, you have an 11F10, you have a triple sum. Can that be interpreted with these Galois representations?
Well, yeah. So actually in the paper I mentioned with Jenny Fuseli and other co-authors, we actually trying to, this is kind of ambitious project, like the classical formula, we want to find a formalism to translate them to the finite field settings. We noticed that a lot of cases we can do it, but some cases, if it's involving something additional, we cannot do it. But my experience is for other further generalization of Whipple's formula, what they're actually, on one hand side, telling, the version I'm actually mentioning will be some other version. It's 9FA. You permuting around the parameters, you get to another 9FA. For those versions, I'm pretty sure there are finite field analogs. For the one you mentioned about triple integral, I think it's pretty much that there might be, my feeling is there might be finite field analogs. Right? Yeah, thank you for mentioning that. Yeah, this is actually, yeah, those, of course, that I mentioned at the very beginning, there are so many formulas. We would like to see what kind of information we can read from those formulas. This is more or less the project we have been trying to do. Actually, things from the WIN project several years back. Then I get into hypergeometric from over there.
Any other questions?
I can ask a question here. I don't know if this is a good question or not, but like these truncations of these 6F5s that you have here, do you think that those have anything to do with integrals like this integral of this modular form here? Like, say for a large prime P, is that somehow related to some related integral like the one here, or?
They are actually, they are kind of analogs of the Hasse invariance for elliptic curves. And for the truncation, it's not directly, it's kind of funny. It's that if you get the untruncated version, it encodes all the information at all p's, because if you truncate, then you get what happens at p, right? It's kind of convenient that for the untruncated version, if you want to get the finite information, you just do the truncation. And the other thing is, it's not exactly kind of directly translated to the version down there. However, there is the p-adic analog, which is the walk, p-adic hypergeometric functions. What he used is, this is the starting point for his p-adic hypergeometric function. He used consecutive ratio. It's truncation that you p minus 1 at the first one, then p squared minus 1 will be the second one, p to the 3 minus 1, and then he take the consecutive ratio. And if you happen to get into the ordinary case, that means that in the case if left-hand side is not going to be 0 modulo p. And if you use the walks kind of notion, if you take the truncation p to the s minus 1 over the previous truncation, what you will get to, it will be exactly the p-adic unit root of this AP coefficient on the right-hand side. So it will be precisely, the limit goes to there are AP now is the sum of two values, right? Because it's actually the trace or it's the second term for the Hecker polynomial. So it's a t squared minus AP for this case plus p to the 5. If you solve it over ZP, there are two roots. Ordinary case tells you that there is a p-adic unit root. The other one will be p to the 5 over the p-adic unit root. The walks version precisely tells you the description for the p-adic unit root. So this is exactly the non-Archimedean version. It's going into the, if you look at the L function, it's the local Euler p factor. It appears in the local Euler p factor. It's called the p-adic period somehow. So it's the analog for the period down here. And the walks version only tells you p modulo p to the 1 power. It's much weaker than supercongruence. That's why supercongruence is super hard. The walk only tells you this congruence modulo p. But if you want to get to p to the 5, then you have to walk 4 more stairs to go up to there. Yeah. Any other questions?
Yes. Any other questions?
I have one final question. Is there a finite field version of elliptic hypergeometric functions?
It depends on whether you call what I mean, if we go back to, yeah, it depends on the, oh, it's pretty slow. It's actually, I mean, what we actually trying to write down the dictionary between the classical and the finite field setting is every time in a classical setting you see like an integration, you turn that into a appropriate submension. And then if you have something which is, this is a multiplicative character, you turn into multiplicative character, additive character, you turn into additive character. So there is a concrete way you can actually kind of write down the classical formula using the dictionary. So some of them makes good sense. So, yeah. And then it's in the same spirit. You can write down the formula from this way as well. It translates essentially rational number into characters. The way you write into characters will be you start with A, which is a rational number. As long as you know the denominator is controlled, you can turn that into a character by fixing a multiplicative generators for the set of all multiplicative. Yeah, fix the generator omega, and then you let omega raised to this power, you get a character. And then you can turn the gamma function into Gauss sum. So the project was, we're trying to do something like a calculus style. If you have everything in the classical setting, we have a dictionary, and then some of the identity can be translated directly. Some of them cannot. Whipple's formula, I cannot do directly because if I do it that way, I lose all the geometry in the background. So this approach somehow let us to discover what's the geometry in the background, so that I know the right-hand side is a sub-representation of the left-hand side. It's a different kind of approach then. It's more geometric for this current paper.
Mm-hmm.
Great. Any other questions?
Well, thank you again for the opportunity.
I have a quick question going back to the integral formula theorem. I think you said it, but I missed it. Did you say that those types of formulas are true or expected for all of the hypergeometric things on your list?
Yeah, in my paper, we listed a few more. Okay. And I think that general philosophy actually tells you, so while we're doing all this, it should be compatible. If you see a rainbow here at Baton Rouge, you might see it somewhere in Atlanta, right? If we're close enough, if we are related.
Okay.
Yeah.
Are the geodesics you're integrating over the same in each case, or are they different?
It's actually the past, the way to unravel the past. In the actual proof, the past is we start with write everything in terms of modular function. And then we set the modular function, the value to be 1. So it's actually do the integration along a circle if I turn the parameter into a modular function. And then we unravel the path into tau. It turns out the path corresponds to this path. Yeah, it's actually more geometric to write down a complete circle in terms of elliptic function.
Great. All right. If there are no further questions, let's thank Ling again.
All right. Thank you. All right. Any questions, you can send me email then. Appreciate that. Okay, bye.